Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Evencio Mediavilla and Jorge Jiménez-Vicente with us today. Hi, Evencio. Hi, Jorge.
Hi, I'm Evencio.
Hello, Frank. Hi, I'm Jorge.
Very nice. Where are you guys located?
Well, now we are in Granada, but I'm from the Canary Island, and now I'm visiting Jorge here to work in gravitational microlensing.
Very cool. Very nice. I've been reading some news reports, and it seems like at least in parts of Europe, it's gotten quite hot this summer. How's the summer going for you guys?
It's been pretty hot. Here in Granada, it's usually hot. Well, for Spanish standards.
Nothing special.
Phoenix is a particularly hot place, but yeah, we hit nearly 46 this August.
Ooh.
So pretty hot.
That
Only
is
for a couple of days, but yeah.
Wow. 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 That's even hotter. I'm in Phoenix, and it is September 8th, 2021. And we'll go out a little cooler today. We'll probably at 39 today, 40 C. So definitely a little bit cooler than what you're getting at 46. Boy, that's hot.
It was only a couple of days, fortunately. So we are now at a quite comfortable 31, 32.
Oh, winter. That is, Jorge, that is a very awesome shirt you have on there, microlensing. Very cool. Did you have that made, or was that part of a conference or something? Or
I actually enrolled in a course to learn cutting machines for making t-shirts and stuff. So this was part of my practice. I designed and made my own t-shirt.
Oh, very cool. Very nice. Okay, so anybody who wants a microlensing t-shirt, you know where to go.
Yeah.
Very cool. Very cool. Okay, so Evencio, Jorge, what do you guys like to do for research?
Well, we started working in lensing, in gravitational lensing, gravitational microlensing in quasars. To be more specific, we apply gravitational microlensing like as a tool in several different scenarios, trying to study, for instance, the temperature distribution in quasars, or also the dark matter, no?
Yeah.
And things like the primordial black holes and so on.
Cool. Very nice. Very good. And that is going to bring us to this very lovely APJ article, Testing Einstein's Equivalence Principle and its Cosmological Evolution from Quasar Gravitational Redshifts. And Evencio and Jorge, take us away.
Well, we wrote this paper because we have found a method, a different way to estimate the gravitational redshift of the accretion disk in quasars. And then we were willing to apply this new method to any interesting problem in astrophysics and cosmology. And we started, in fact, to apply it in quasars to estimate the mass of the black hole, the supermassive black holes. And we compared the results with the results obtained for masses from the Virial theorem. And we have published 3 papers in Astrophysical Journal about this issue. And then we realized that with this method, we can also explore the possibility of testing Einstein equivalent principle in the cosmological realm, further away of zeta equal to 0, basically. That is the region of the universe where this principle has been probed till now.
So maybe if you can show figure number 1, it's a good starting point, because we can see what was the situation before this paper and this equivalence principle testing. Because yeah, in this figure we see that this equivalence principle was pretty well established in the nearby universe. We have in the upper inset the measurement of the ratio between the measure versus the expected gravitational redshift. Well, from the ground experiments, the famous Pound and Repka experiment in the Harvard Tower, till experiments in the Sun or in Sirius B, or even the star S2 around the galactic center. And in this context, this was pretty well established, but in a, let's say, cosmological extent, the experiments were very few. Actually, only a couple of experiments measuring the gravitational redshift in galaxy clusters, trying to measure tiny effect of few 10 kilometers per second between the galaxies in the outskirts and the galaxies in the inner part of the galaxy cluster. So it was very challenging experiment, and it was only done for a couple of clusters at a redshift of around 0.2. So the cosmological playground, yeah, it was only still the nearby universe. So we have, let's say, opened a new window by measuring gravitational redshifts much farther away, and doing it in a scenario that was, it is much more favorable to measure gravitational redshifts, which is in accretion disks around the massive black holes in quasars.
Okay.
Because there you expect a very rapidly changing gravitational potential. So, in principle, you could expect gravitational redshifts of 1,000 kilometers per second, which should be pretty easy to measure in principle, but it's also very challenging because the broad lines in quasars come from much larger regions. So you have to find some chemical species that it emits only close to the black hole.
Okay.
And this is
then is when gravitational microlensing enters into the scene, because we observe that a very humble feature in the ultraviolet spectra of quasars is a feature, a blend of the iron-3 in the ultraviolet. We notice that is is highly magnified by microlensing, with amplitude comparable to that of the continuum. And then, as far as microlensing is going to be sensitive to the size of the emitting region, in the sense that if you have a small emitting region, microlensing is going to be very high, then we suspect that this region, the region emitting the iron-3 ultraviolet emission, is tiny, is very small, comparable to that of the continuum, that presumably is the accretion disk. And then we fit a template, a very famous template from Westergaard and Wilkes of the iron-3 emission. Perhaps we can go to the second figure in the appendix.
Yes, and we got our narrow and black composites right there.
And yes, in this we can see the number of individual lines that form the blend, and we see how we fit with this template very good. No, it's a very good fit, the one we obtained for the narrow emission, and then when we fit all this blend, we notice that systematically in all quasars the fit, well, the blend is redshifted with respect to the theoretical, to the template, you know? And then we made the hypothesis that the redshift is of a gravitational origin.
Okay.
And this idea, this hypothesis, has been posteriorly confirmed or supported by a study, a photoionization study made by Temple and collaborators that estimate that the iron-3 emission in the ultraviolet is confined to a region very close to the to the supermassive black hole.
I'm with you.
Then we have this and other evidences supporting the idea that the iron is coming from the accretion disk. This iron emission is coming from the accretion disk. In the appendix, we are not going to talk about this, but in the appendix, there is a detailed explanation in extenso of these evidences. No?
Yes.
Then, once we have this measurement of the redshift based in this fitting this blend, we can prepare an experiment to measure the equivalent principle that is basically the iconic one, the one that people uses to determine, to study, to test the equivalent principle in the solar system or in other stars in our galaxy. With the difference, perhaps we can come back to the introduction of the paper.
Figure one, you want the introduction? Okay, let's go to the introduction.
Yeah. Yes, and then we propose to compare the observed gravitational redshift with the theoretical one, and this is always the typical experiment to determine to test the equivalent principle, and with a difference, because our emitter are not static, but they are moving in circular orbits around the supermassive black hole. And then we need to take into account another effect, which is the transverse Doppler. But well, this is not difficult to take into account. I think that in the equation number 2 or 3, we can see the expressions, the formula, which are very simple. And then that we have our observable is the ratio in equation 4 between the measured gravitational redshift and the predicted one.
Okay.
So the game at play here, it's in principle on the paper, it's pretty easy. We just have to measure redshift in a certain spectra and try to calculate the expected value for that redshift. The problem here is that to calculate the expected value, we need two numbers which are not easy to get. One is the mass of the black hole, of the supermassive black hole,
okay,
and the other is the size of the region emitting this iron blend.
Okay.
So yeah, for the mass of the black hole, there are a couple of methods to calculate, but probably the most often used is using the virial theorem. We assume that the gas surrounding the black hole is more or less virialized. So by measuring the widths of those broad lines, you can get an estimate of the mass if you get also the size of the region, right?
Right.
An unknown factor here, which is usually called the virial factor, this Fx equation number 3, which accounts for all the unknowns in the system, unknowns in the geometry, the inclination, for example, or whatever, but also in the possible more or less peculiar kinematics. Right? So yeah, but it can be estimated by measuring the widths of some spectral lines, right?
Uh-huh.
The ratio of the measure redshift with respect to the expected one is a number that depends on observables, except those two that we have said. The size of the iron emitting region and the virial factor, right? For the virial factor, it's tricky to estimate. We've made a quite thorough review of the literature to try to get possible best estimate by averaging up to, I think, 10 different studies. So, but roughly, let's say that if we use the full width of maximum as a measurement of the width of the line, these have number for most used species, like for the H beta line or for magnesium 2, whatever, is a number around 1.
Yeah.
Be slightly below 1, but pretty much that one. And then the other tricky thing is measuring the size of both the iron emitting region of the line that you are using. It could be H beta or magnesium or whatever. Maybe eventually you can tell us how we estimate the size.
Yes, to estimate the size of the region emitting the strong, typical strong emission lines, H beta or H alpha, we use the typical relationship from Benz, which is very famous and is widely used. But for the region emitting the iron 3, we need to prepare our own size luminosity relationship with the same shape than the size luminosity relationship by Benz, but now we use the luminosity closer to the region where to the spectral wavelength of the iron emission, and also we estimate, we base our calibration of this relationship in some measurements of a group of gravitational lenses where the size of the region emitting the iron 3 could be estimated from microlensing amplitude. No? Then we anchor our relationships to this group of objects that have been studied by Fian and collaborators.
Cool. Very good.
So, what we did was to try to get this ratio between the measured and expected gravitational redshift for a couple of available quasars for which we had good enough quasar spectra, right? First set was a set of quasars observed with the X shooter at the VLT that have very good signal to noise, and that have virial masses estimated and measurements of the widths for several spectral lines, and in which we could fit this iron blend quite well. But we also applied it to 85, if I remember correctly, spectra from the SDS, from the Sloan survey, and also to
I can make a point very interesting that we forgot to mention before, is that we are able to calculate the gravitational redshift from a single spectra from the Sloan Digital Sky Survey, which is an interesting result, no? And also we can do individual estimates of masses from this single spectra corresponding to a single object.
Yeah, exactly. That's true, because people doing this in cluster of galaxies, they get a measurement for the whole cluster. We can do it for single galaxies, which is can be very helpful in many cases. And yeah, we did this for a couple of data sets. There's X-shooter spectra, but also for Sloan spectra, for very extremely high signal to noise composite spectra from the Bose spectrograph. And we'd also do this for let's say, anchor also things of low redshifts for two individual active galactic nuclei in the nearby universe, for which we were able to also estimate this gravitational redshift and all the other necessary numbers. So if we go back to our figure 1, we can see that we were able to measure this ratio between measured and predicted gravitational redshift that tests the equivalence principle for a set of objects in a cosmological redshift range between 1 and nearly 3, which covers yeah, quite back in the history of the universe, nearly 10 gigayears ago. So it opens a complete new window to test this sort of things in a region of the universe which was pretty much forbidden before. So it actually, we were able to measure this ratio in a region that was previously unknown, and with a accuracy which is comparable to what people have done, at least close to the galactic center, not in solar system or in a very nearby universe. But yeah, very competitive, and particularly compared to the extragalactic other extragalactic works. You think?
Yes, yes. And then we obtain some interesting results. No, perhaps the most interesting result is the ability of the method to test the Einstein equivalent principle. But we have also some practical results, and we see from this figure that we can test, we can prove the equivalent principle between approximately redshift 1, cosmological redshift 1 to cosmological redshift 3 with about 20-25% of scatter, which is not bad. Mm-hmm. But we can try to reduce the scatter by grouping the data in other bigger windows of redshift, and these are the red data points in our figure, and then the scatter is reduced to about 10%. Yeah. And if we want only to have a measure for all the studied range between 1 and 3, then we obtain a test to the Einstein equivalent principle with an uncertainty of only a 6%. Okay. This is the good point, no? But this is there is a problem. Well, it's not exactly a problem, but this is a consequence of having some parameters like the virial parameter or the radius of the region emitting the iron 3, and these parameters are not very well determined. Then we have a systematic uncertainty to add to our data. No? And this systematic uncertainty can be mitigated doing some things. We can obtain more data. We can try to improve the value of the virial factor, or knowing better the size of the region emitting H beta or the iron. But an interesting point is that we can consider this from the perspective of the null redshift experiment. We can compare the results in any of these redshift, at any of these redshift with the rest of the results. We can say, for instance, having the same numerical factor for the ratio between the iron, the sizes of the iron and the H beta region, and the same virial factor, then the systematic error is the same for all the redshift beams. And then the relative change of the Einstein equivalent principle between redshift 1 and redshift 3 is independent of this systematic error source. And this is the good point of this experiment. Can be transformed in a null redshift experiment like many others that can be done in the solar system to obtain the best test of the equivalent principle.
Very nice. So, well, there are some, of course, technicalities in the paper or whatever. I think that's the main conclusion of the paper, that gravitational redshift can be measured quite back in the history of the universe. We have done it up to redshift 3, but in principle, if you get a spectra, for example, in the near infrared, it can be done at redshift 6, 7, yeah, you know, as far as you can get a good signal to noise spectrum. And if you improve also the quality of the data and you get a better knowledge of a few of these numbers, you can actually put gravity to a test quite back in the history of the universe. So this is actually possible by measuring this gravitational redshifts in quasars.
Yeah.
Another interesting thing is, well, we can also point out that we have been here referring to the Einstein equivalent principle. But in fact, when you make a redshift test and you involve 2 points which have a non-constant gravitational field, the gravity at where the photons were emitted in the quasar is very much larger than the gravity here, no? Then you can also test the metric theories of gravity, not only the equivalent principle. If you measure the change in a tower, no, in a city, then as far as the G is going to be constant, you can only prove the Einstein equivalent principle. But if you measure the redshift in the sun, or in a star, or in a quasar, you can also test the general theory of relativity or other metric theories. And also we can try to think about this in the future.
Awesome. Very cool. Very cool. Nice work. Well, Evencio, Jorge, I want to thank you both very much for walking us through your very lovely paper. And you hinted at it a little bit there at the end. And so where do we go, let's say, over the next 5 years? Are there additional, do you have additional observational campaigns going, telescope time, to get more samples in that 1 to 3 redshift range? Or are there other surveys going out there that will take it out to farther redshifts? Are there some new telescopes coming online that would be able to give spectra with a suitable signal to noise to help beat down some of that errors? Is there theoretical work that can be done? Just sort of where do we go over the next, let's say, 5 years?
Well, probably a little bit of everything you said, right? We are planning to get new observations to try to get better data in this redshift range between 1 and 3 by using larger telescopes. Many of these data points have been obtained with the Sloan Digital Sky Survey, which has a 2.5 meter telescope, but we have now 10 meter class telescopes available, which can provide much better data or go farther away in redshift.
Cool.
That's one point. Also, we will try to work a little bit and try to fine-tune those tricky numbers, maybe the size of the iron emitting region, right, which can be done several ways. Most valuable measurement would be we could get a reverberation mapping a lag, measurement of this emission, but that is very challenging. So we have to think it very carefully. And yeah, also trying to fine-tune everything. If we can get the error bars smaller to a place where we can, maybe as Evencio just say, test finer things about gravity.
Yes, we are working also in obtaining a post-Newtonian approximation of this effect in our case, having into account the transverse Doppler in order to know if we can test alternative theories and perhaps to know which precision is needed for doing that. No, but I think that perhaps the first thing that Jorge mentioned about doing reverberation mapping to know to know directly the size of the region emitting the iron is the most challenging option and the most interesting one for the future.
Very cool. Yeah, it'd be very interesting to perhaps rule out various classes, right? F of R gravity being a very common one these days. So that would be very nice. Very cool. All right. Thank you again, guys, for walking through your very lovely paper. And thank you, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Thank you.
Bye.